All right, let's get started. All right, so welcome back to another Math 230 and 230 GSG session. Again, I apologize for the delay in this upload. I had some connectivity issues last night. So yeah, all right, so let's see. So for today's session, I'll be covering more examples from sections 15.7, 15.8. So I'll be covering triple integrals in cylindrical and spherical coordinates. Yep, and this should help you out for this week's homework. So, okay. Again, I'll be referring to these questions from the textbook, so feel free to look at them after. All right, so let's start off with 15.7. So yeah, some things to note about 15.7, which I'll just write down, is that for 15.7, we want to keep these equations or conversions from cylindrical coordinates to rectangular coordinates. So where we have x is equal to r cosine theta, comma y is equal to r sine theta, while z is still equal to z, and where r squared is equal to x squared plus y squared, tangent theta is equal to y over x, and finally z is equal to z. Okay. So I'll be using a lot of these equations for the examples I've pulled up from 15.7. Okay. All right, so yeah, let's go straight to it then. So I'm going to start off with 15.7, number 12. Okay, so for number 12, yeah, it tells us to sketch the solid described by the given inequalities. So in the question, they give us that theta is in between 0 and pi over 2, while the radius, or r, sorry, is less than z and less than 2, or rather z is in between r and 2. Okay. So what I can do first is I'm just going to focus on this side of the inequality. So I'm just going to label this as 1. So start off with 1. So number 1, what I can say is that we have an upper bound of z at the plane z is equal to 2 as my upper bound, while my lower bound is going to look something like r is equal to the square root of x squared plus y squared, which is also equal to z. So this is going to be a cone facing upwards for my lower bound of the inequality. So we'll have something like this as our inequality. See if you can draw this. All right, so I'm just going to do something like a cone. Yeah, something like that. While it intersects the plane at z is equal to 2. Okay, so just imagine there's a plane across at z is equal to 2. Okay. All right, so that's inequality number 1, or where z is in between r and 2. Okay, so now let's look at the first inequality, which specifies that theta is in between 0 and pi over 2. So what we have is that this cone right here facing upwards is condensed into the first octant. So if I actually condense this down, I could say that we're only gonna care about this side of the cone, right? Because since theta is this angle right here in the xy plane, we're just gonna focus on the cone in between 0 and pi over 2, okay? So yeah, so for question number 12, this is actually what it's roughly gonna, what the solid is roughly gonna look like. All right. Yeah, and due to the late upload, just feel free to message me for any questions on Piazza once you see this recording. Okay. All right, so let's move on to number 18 from 15.7. So 15.7, number 18. Okay, so let's see what we have at number 18. Okay. So yeah, for number 18, we're gonna look into solving actual triple integrals using cylindrical coordinates. So what they give us is they specify that we have the triple integral in a closed region of E with function z times dv. And what we're supposed to do is we're supposed to solve this triple integral using these cylindrical coordinates. So we'll have dv as r dz dr and d theta for this part of my integral. Okay. All right, so I'll just leave that for now. And oh, and z is gonna look something like x squared plus y squared. Okay. Yep. Or sorry. No, z actually stays the same. Yeah, z actually stays the same because we have an integration variable, obviously. All right, so now let's look at the bounds. So let me start off with what they give us. So they give us that it's that region E is enclosed by the paraboloid of z is equal to x squared plus y squared as our first constraint, and the plane where z is equal to 4. Okay. Yeah, this is usually the hardest part of the question, which is the setup of the bounds of my integrals. So based off this, we can say that z is in between r squared, because what we can say is for this equation right here, this actually ends up being z is equal to r squared plus, or is equal to, sorry. This is r squared, which is equal to x squared plus y squared. So this is going to be my lower bound for d of z, while this intersects the plane at z is equal to 4. So this is going to be my upper bound. So for this side of the graph, or yeah, for this side of the graph, we can say that z is going to be from r squared, or yeah, this part of the integral is going to be from r squared up to that plane of z is equal to 4. Okay. All right, so the next thing we need to find is the r and the theta. All right, so from this question, it also specifies that z is equal to 4. So this intersects these two equations, these two planes intersect when x squared plus y squared is equal to 4. So what we can see from this is that we can see this is an equation of a circle in the xy plane. XY plane. And we know what we know about the circle in this xy plane is that it has a radius equaling to 2, right? Since r squared is equal to 4, so radius is going to be equal to 2. And what we know about this circle is that, yeah, there are no constraints in terms of the theta value. So we're considering the whole, the whole region. So what we can deduce is that for d of r, my lower bound is going to be from 0, right, all the way up to the radius of 2, while for d theta, my integral is going to be bounded between 0 and 2 pi. So yeah, that's going to be the setup of solving this question using cylindrical coordinates. Okay, so let's actually solve this triple integral. So we have 0 to 2 pi, and then I think it was 0 to 2, yeah, 0 to 2 and r squared to 4. 0 to 2, then r squared to 4 of z and d r d dz dr d theta. Z dr d theta. Okay, so let's look at the first integral. That's going to look something like pi 0 2. It's going to be 1/2 z squared r, 1/2 z squared r, from r squared to 4. Then we have dr d theta. Then that is going to equal to 0 to 2 pi, 0 to 2, and then if you solve this, if you compute this out, we get 16, so 8r minus, so if you plug in r squared, it'll be half of r to the power of 5. Then we have dr d theta, and then 0 to 2 pi of dr is going to be 8r squared over 2, so 4r squared minus 1/2, so 1/12 r to the power of 6. And then this is going to be computed from 0 up to 2 with d theta. Extend this out, it'll be from 0 to 2 pi of 16, so it'll be 416 minus to the power of 6 is going to be 64 divided by 12. It's going to give me, okay, so I'm just going to leave it as a fraction. 64, 12. Yep, and then minus 0. So I'm just going to leave it as that. And then the theta, then that is going to equal to 16 minus 64 over 12 theta, computed from 0 to 2 pi. Right, and I think you get the point from there, which is 16 minus 64 over 12, 2 pi. Okay. So yeah, maybe later on for the next few questions, I won't actually solve the triple integral. I think I'll get through the hard part of setting up the integral. Okay, but if you have any questions for anything, just feel free to contact us on Piazza. All right, so that was number 18. All right, let's get on to the next question. So let's look over number 20. All right, so 15.7, number 20. Okay, so same question, evaluating with cylindrical coordinates. So we have the triple integral of e x minus y dv. And we're supposed to convert this into spherical coordinates. So that's going to be r dz dr e theta. Okay. Since we know that x is equal to r cosine theta, while y is equal to r sine theta, we can say that this is going to be r cosine theta minus sine theta. Okay. All right, so let's start by looking at what E stands for. Okay, so E is the solid that lies between the cylinders x squared plus y squared is equal to 1, and it's above the plane of z is equal to 0, and finally it's below the cone, below z squared, or sorry. Oh, okay, I copied that down wrong. So it's actually Sorry about that. Yeah, it's actually between the cylinders, x squared plus y squared is equal to 1, and x squared plus y squared is equal to 16. Above xy plane, y plane, and finally it's below z is equal to y plus 4. All right, so I can start off with these two equations right here, right? So it actually specifies the cylinders that we're enclosed in. So for the first part of this question, I'm just going to look at x squared plus y squared is equal to 1 and x squared plus y squared is equal to 16. So what we can deduce is that the radius is actually going to be bounded between 1 and 4 based off these two equations. Now, the next thing they specify is that the z value is going to be based off the second part of the constraints they give us. So for number 2, since you're going above the xy plane, that's basically when z is equal to 0, right? So what we can say is that z, can pull this up, z is going to actually be bounded between 0 and y plus 4. But you can further or expand this out. You can represent y in terms of r. So you could say that z0 or z is in between 0 and r sine theta plus 4. Okay. And finally, the third part, which is theta, is that since there are no constraints on that, and we're considering the whole solid that lies between, or this whole solid of E, the whole solid region of E, we can say that theta is going to be in between 0 and 2 pi. So our setup for this question is going to be the integral of r squared, r squared cosine theta minus sine theta of dz, dr, d theta, and then dz, as we specified, goes from 0 to r sine theta plus 4. Yeah, and one thing you want to do is you don't want to keep it as y because you have integrating variables are in z, r, or theta, right? So you want to convert it to something in terms of a radius or r. And so r is going to be in between 1 and 4. And finally, theta is going to be enclosed from 0 to 2 pi. Okay. All right. So yeah, if you can, just gonna leave that setup right there. Okay. Yeah, feel free to try and solve that integral out. Okay, so yeah, let's move on to the next question. Yeah, let's go and let's look at number 21 next. So we're looking at 12 points or 21. Sorry. Number 21. Okay. So number 21, same thing. You want to look at now you want to look at x squared dv, and it specifies that the solid lies within the cylinder x squared plus y squared is equal to 1. Above the plane z0, above the plane where z is equal to 0, and finally below the cone, below z squared is equal to 4x squared plus 4y squared. Okay. Right, so first thing I would do is I would look at the z values and look at what they're bounded between. So I can say that since z squared is equal to, so I'll actually look at this part of the constraint they give us first. So, okay, number 1. Okay. So what we can do is that first we know that z has to be greater than or equal to 0, right? Because since we're looking at the solid region above the plane where z is equal to 0, but what we can do about z squared is equal to 4x squared plus y squared is we can simplify this down. We can simplify this, or 4y squared, we can simplify this down to z is equal to the square root of 4, I'm sorry about this, is equal to square root of 4x squared plus 4y squared, which can further simplify down to square root x squared plus y squared. And finally, we can rewrite this as 2r, right? Again, you want to make sure that all your values are in cylindrical coordinates, okay? So we can say that z is bounded between 0 and 2r. And then finally, what we want to look at is we want to look at this part of the constraint they give us between the cylinder x squared plus y squared is equal to 1. Okay. So what this implies is that we're looking at the cylinder. X squared plus y squared is equal to 1. And so this has a radius of 1. So we can say that R is constrained or bounded between 0 and 1. And again, theta would have to include the whole circle. So we're going from 0 to 2 pi. Right, so if we set this up, the triple integral is going to look something like this. So if we have x squared, that's going to be r squared cosine squared theta of r. And then we have dz, dr, d theta. And so z is going to be bounded again, as we said, it's from 0 to 2r. R is going to be bounded from 0 to 1. And finally, theta is going to be from 0 to 2 pi. So this is going to be our setup for the triple integral. Okay. All right, so that was number 21. Let's go to the next question then. So let's look at 29. And I think this is going to be my final question from 15.7. And so we'll look into spherical coordinates next. All right, so for number 29, so we have 7, 29. Okay, so it actually gives us the triple integral in rectangular coordinates. And we're trying to change this into cylindrical coordinates and solve it that way. Okay, so they actually give us -2 to 2, negative square root of 4 minus y squared, up until square root of 4 minus y squared. Finally, from square root of x squared plus y squared, up until 2 of x z of dz dx and is it dx? Yeah, dx and then dy. Okay. So trying to solve it using cylindrical coordinates. We want to convert this. All right, so I'm just actually going to write all the constraints down. So we can say that y is going to be based off this triple integral. It's going to be bounded between -2 and 2. Now, x is going to be bounded between negative square root 4 minus y squared and square root, what is that? Square root, square root 4 minus y squared. And then finally, z is going to be bounded between 2 and square root x squared plus y squared. Okay, so I'm just going to focus on this part of my inequalities, or I'll look at this part of the question first. Okay, it's number 1. Look at the z value, because in cylindrical coordinates you want to write down that dv is equal to r, dz, dr, and d theta. Okay, so let's see. So z is in between. Oh, sorry. Yeah. Okay. Yeah, so we can say that z is greater than the plane where you have x squared plus y squared, which is also the same thing as r, right? Because r squared is equal to x squared plus y squared. And then, yeah, z is less than or equal to 2 stays the same. So what we can say about z is that in cylindrical coordinates, we want z to be greater than r, and we want it to be less than or equal to 2. Now let's look at the other parts of the equation. Okay, so now we want to look at the radius. And the radius, or I'm actually going to look into both of these inequalities for the second part of this question. Now, based on the inequality for x, we can formulate this equation of a cylinder of x squared plus y squared is 4, right? And further specified with y is in between 2 and negative 2. So that's in the xy plane, that's actually going to look, that's actually going to look like a circle with radius of 2, right? Since x squared plus y squared equals to 4 is going to give us a circle radius 2. And since y is going to be bounded between positive 2 and negative 2, we basically have this circle. And this can translate into your dr and your d theta. So what we can say is that the radius is going to be bounded, or r is going to be bounded from 0 to 2, while theta is going to enclose the whole circle. So it's going to be from 0 to 2 pi. Okay. So if you set this up in cylindrical coordinates, I'll set it up and I'll move this a bit upwards. So r is going to be, again, I think we specified as 0 to 2. And then theta is from 0 to 2 pi. Okay. So we set this in triple integral in cylindrical form or coordinates. That's going to be from r to 2, right? Z doesn't change too much. Now, okay, let me just specify what x is first. X is going to be r cosine theta. So it's going to be r squared cosine theta of z, dz, dr, and d theta. And that r squared comes from the extra r from dv. Okay, okay, so dz is going to be from r to 2, dr is going to be from, or r is going to be from 0 to 2, and finally theta is going to be from 0 to 2 pi. Yeah. So yeah, I think that should wrap it up for the questions I have prepared for 15.7. All right, so let's move on to 15.8 then. So for 15.8, I want to write a few important things which should be noted. So again, the conversions between rectangular coordinates and spherical coordinates this time. So it's going to be x is equal to rho sine phi of cosine theta, and then y is going to be rho sine phi, sine phi sine theta, and finally z is equal to rho cosine phi. Okay. And this is based off the two triangles covered in lecture, so feel free to look at that. And then finally, rho squared is equal to x squared plus y squared plus z squared. Okay. Now, the triple integral is usually going to be set up in this way, where we have a closed region and then a function specified in spherical coordinates. Well, this part, or dv, is going to look something like rho, or it is going to be rho squared sine phi d rho d of theta, and finally d of phi. Okay, so this actually represents d of phi. Okay, so yeah, I just want to just write those few notes down. Then let's just go straight into questions. So let's start off with number 22. Okay, let's see. Okay, So yeah, we're just going straight into solving triple integrals using spherical coordinates. So we start off with triple integral of bounded with e, and we have y squared, z squared, and dv, where e lies above the cone, phi is equal to pi over 3. So above cone and below sphere. Sphere of rho is equal to 1. Okay. All right. So yeah, I think we're pretty much done with this. Yeah, they specified basically everything we needed for this question. So yeah, if we could to convert this, that's gonna look something like, so y is gonna translate into rho sine phi, sine theta squared. Z is gonna convert into rho cosine phi squared. And then we have dv, which is rho squared sine phi, d rho, d theta, and d phi, phi, d rho. Okay, and then our bounds is as specified. Rho is gonna be below sphere, rho equals 1, so it's gonna go from 0 up till 1. Theta is always gonna, or it doesn't specify in this question, so we're assuming it's gonna be from 0 to 2 pi, which is the whole circle. And then phi is gonna be from, it's gonna be above the cone. Phi is equal to pi over 3, so from 0 to pi over 3. Okay. Okay, so just double check that. Okay. Okay. All right. Yeah. So that's it for the setup. Yeah. Okay. All right. So let's actually solve this one. Yeah. We'll go through one question, solving the whole triple integral. So what we can do with this is we can actually split this up into 3 integrals. So I think covered in lecture with with Joe, you can split up, or let me simplify this down first. So that's gonna be rho squared, sine squared phi, sine squared theta, rho squared cos phi squared, and rho squared sine phi. Okay, so what we can say is we can group up all the rows together, right? So it's gonna be rho to the power of 6. Or wait, sorry. This is not rho. This is supposed to be phi. So for phi, we have sine squared phi and cosine squared phi and sine phi. So that's gonna look something like sine cube of phi, right? And then we have cosine squared of phi, d phi. And then for the second part of the integral, it's gonna be from 0 to 2 pi of sine squared phi, or theta, sorry, d theta. And finally, it's going to be from 0 to 1 of p to the power 6 of dp. All right, so this integral shouldn't be too bad. This one is going to be a conversion using the double angle identity. Right, so this, yeah, and for this one, this might be a parts question. Okay, so let's see. All right, so, so yeah, okay. Let me just start off by converting this. I think the approach I would take for this part are, let's split this up into 3 different integrals. So let me start off by looking into this part, first part. So for the first part, I'm just going to look into the integral of 0 to pi over 3 of sine cubed phi and cosine squared phi. Okay. I'm just using, I think, yeah, this should be using the double angle identity. So I can convert sine cubed phi into sine phi multiplied by oh, sorry about that. 1/2 1 minus cosine 2 phi multiplied by cosine squared phi e phi. All right, if we pull this up, so we would say it was sine phi cosine square 1/2 1 minus cosine 2 phi, and finally cosine squared phi, I think. Yeah, yep, it was cosine squared phi. Okay, and now we're going from 0 to pi over 3 for phi. Okay, so let's see. Expand this out, we get 0 to pi over 3 of sine phi. Yeah, this might be a U-sub question, so yep, 1/2 or it'll be cosine squared of phi divided by 2 minus cosine squared of cosine 2 theta. So yeah, cosine squared phi of cosine 2 theta over 2 d phi. Okay, so solve this out. I'm just going to split this up into two different intervals. So from 0 to pi over 3 of sine phi cosine squared phi 1/2 d phi plus 0 to pi over 3 minus 1/2 minus cosine squared of phi, and then cosine of 2 phi d. Okay. All right. Or yeah, oh my bad. Yeah, I wouldn't use the double angle identity. I'll just use 1 minus, yes. Okay, I don't want to use that identity. I definitely do not want to use, yeah. Okay, so that was my bad. For sine squared phi, instead of 1/2 times 1 minus cosine 2 phi, I can just use sine squared plus cosine squared is equal to 1, right? So if we simplify that down, that's going to be 1 minus cosine squared. Yeah, that should make it a lot easier for this question. Okay, so yeah, I think pretty much that's it. Yeah, okay. So going back, let's, oh, there you go. Okay, so 1 minus cosine squared, let's erase this. Let's look into it, so that'll be 1 minus cosine squared phi. And then for this part, it will just be sine phi times cosine squared phi minus cosine to the 4th phi. Okay. So yeah, that should make it a lot easier. Oh wait, no, that stays the same. So that's just cosine squared phi d phi. Now this 1/2 is taken away. And then we have 1/2 taken away. That's minus. I'm just going to pull that out to here. Then we have cosine squared phi, or no, it'd be sine phi times cosine to the power of 4 phi. Okay, so if I erase this, so yeah, it'll just look like a U sub question for this question. So that'll be sine phi of cosine to the power of 4 phi d phi. So let's solve it out using U sub. That's going to be 1/2 cosine, yeah, U 1/2 cosine squared. So that's going to be U. It's going to be actually be a third cosine third phi, right? Minus from 0 to pi over 3, because if you take the derivative, should be 3 cancels out, and then cosine becomes a negative sign, so that should be a negative up there. And so that's going to be subtracted with U sub again. That'll be 1/5 this time, and that should be a plus of cosine fifth of phi from 0 to pi over 3. Okay, and if you, again, if you derive this, it's going to be cosine power of 6, 4, 5. Yep, that works out. Okay, so let's actually compute this out. 1/3 of, so cosine 0 is going to be 1. So that's cosine pi over 3. That's going to be 60 or 1 square root 3. So that's going to be 61 over 2. Okay, 1 over 2. 1/3, 1 over 2 minus 1 plus 1/5 times, again, or 1 over 2 cubed. Sorry. Cube. Yeah, 1 over 2 cubed, and then this one is going to be 1 over 2/5 minus 1. Okay. So that is going to be my final answer for this question. Okay. Yeah. All right, so that's basically how to solve triple integrals in spherical coordinates. So let's do, I think I have one more prepared for today. So let's go over number 25. Okay, so number 25, we have triple integral of e, then x to the e. Oh, okay, x squared plus y squared plus m squared of dv, right? And it specifies that the portion of the e is the portion of the unit ball x squared plus y squared plus z squared is less than or equal to 1 that lies in the first octant. Okay, so it also specifies that you're looking at the region in the first octant. Okay, so for number 25, we can say that rho is actually going to be in between 0 and 1 because, yeah, based off this inequality right here, so let's specify as 1. Okay, so we have that you're going from 0 rho squared of 1. So that's just going to end up from 0 rho 1. And yeah, that rho squared just comes from the fact that rho squared is equal to x squared plus y squared plus z squared. Right, so that's from number 1. And then the part 2 of this question, which is the first octant. Okay. So the first octant is basically going to specify that theta and phi are both going to be constraint from 0 to pi. Or 0 to pi over 2, sorry. And phi is going to be constrained between 0 and pi over 2. Okay, so if you convert everything into spherical coordinates, our equation should look like, or our triple integral is going to look something like this. So x is actually going to be phi, or rho sine phi cos theta, e to the power of rho squared, and dv is going to be the same thing as rho squared sine phi d rho, d theta, and d phi. All right, so we said that rho is going to be from 0 to 1. Theta is going to be from 0 to pi over 2. And phi is going to be from 0 to pi over 2. And again, these two are just from the fact that we're looking at the first octant. Okay, so yeah, that should be the setup for this question. And I won't go through the steps for that, but feel free to ask me any questions if you have some. And then finally, oh, actually, yeah, that's not the last question. I do have one more, which is 41. Yep, and this is the same thing we covered for cylindrical coordinates, where we were given a rectangular triple integral. Now we had to just change it to spherical coordinates and solve it that way. Okay, so I'll go through the setup for this question. So we're given that x is going from 0 to 1. Then you're going from 0 to the square root of 1 minus x squared. And finally, z is going to go from square root of x squared plus y squared up till, oh, sorry. Whoa. What was that? Oh.